SpectraMosaic is an exploratory tool developed for the interactive visual analysis of magnetic resonance spectroscopy, or MRS, data. It is the first of its kind to allow comparison of spectral metabolite concentration ratios across multiple dimensions at group and individual levels. This design study for a novel MRS visualization method was performed in close collaboration over several iterations with experts in MR spectroscopy research. For our final design, we gathered additional feedback from MRS research experts in the form of a case study. MRS is a non-invasive biochemical imaging technique utilized in clinical research for a range of neuropsychiatric diseases. Current toolsets for MR spectroscopy visual analysis are limited and often restricted to visualization of spectra for a single voxel for a single patient at a single time, as we can see in this figure. In designing SpectraMosaic, we created a taxonomy of visual encodings framed around spectral metabolite concentration ratios used for key attributes of MRS data that fall under four main categories: cohort, number of spatial voxels, number of acquisition times, and brain state under which spectroscopy was acquired. With our system, we identify 16 potential task use cases highlighted in this figure. For example, Case 9 chose an encoding system for a case comparing spectral metabolite ratios of two patients at a single spatial sample location. SpectraMosaic consists of two main views. The left provides for spectral inspection and customized group creation, while the right serves as a spectral analysis interface in the form of a heat map matrix. With SpectraMosaic, users are primarily interested in assessing group versus individual variation of metabolites in ratio form. These comparisons may be for similarity assessment, where subtle differences are important to track, as well as for large difference assessments such as those seen in tumor studies or in research cases where echo time is varied. Here, we show a Giardia case study acquired with single voxel press, where we look at possible neuroinflammation in 3 different brain locations compared against 2 different patients. Following data preprocessing and quantification in an offline routine, study data are loaded into the application using a drag-and-drop window feature. These data remain linked semantically in the application to ensure continuity between voxel location, its spectral output, and patient-specific information. We see our patient selector panel on the left. Radial buttons allow display of one patient with associated acquisition data at a time. Here, we've selected the first patient, and we can see in the image view the 3 voxel regions acquired for this patient arrayed along this vertical axis. A horizontal axis indicates the number of different time acquisitions performed for this voxel. In this case, we are interested in looking only at one time acquisition. Hovering or selection of each voxel node calls a spectral graph for the voxel below, as well as additional information such as voxel ID, echo time used in the acquisition protocol, and the location. To compare metabolites against each other, we can either select an automatically created group immediately from the metabolite selector panel here, or we can create a more customized group for analysis using the voxel group overview panel. With this view, we can create a custom group and update the membership. We see this membership for custom groups in the bottom right table, which updates automatically. In this case, we're interested in comparing all spatial voxels of one patient to all spatial voxels of the other. Once both axes have spectral metabolites attached, a heat map matrix is drawn on screen. The matrix size is determined by the number of metabolites added as inputs. Users can select a subset of metabolites to review or all of them at once. This drawing updates as the inputs are changed. As we hover over the table cells, we can easily see the metabolites from each axis that are used in the ratio calculations. The height of the metabolite bar encodes, in the case of this group, the median concentration, with whiskers extending to indicate the range for this metabolite. We use a diverging color map. White indicates the compared metabolites are equal, red indicates the x-axis metabolite is greater, while blue indicates a larger y-axis metabolite. Increased saturation indicates a greater difference between the two. Each cell can be expanded to show detailed metabolite ratio information for a given cell. For instance, perhaps we would like to inspect individual ratio variation and voxel variation for region for lactate against total creatine in the study, since lactate is often elevated in Giardia infection. On expansion, we can see that as we hover over elements, associated patient spectra and voxel locations are highlighted in fuchsia in the left view, and the corresponding table row or rows, which contain useful information about the patient voxel sample below. A legend at the right lists key visual elements and maps their shape and color. We can see through the similar hues of the color map that both patients are quite similar between the prefrontal and precuneus voxels. but the hippocampal region shows a large difference, indicating that lactate and total creatine have strongly differing levels in this area. This arises primarily from the female patient, since the male patient had no recorded lactate, indicated by this gray color. We can confirm with the whiskers on the bar's input range for that lactate that causes this variation. However, the red tooltip here indicates that the model fit for this metabolite to the raw spectrum may not be reliable and needs further investigation by the expert. Subtleties like this would be difficult to understand through visualization of the spectral graph or through statistical measures alone. If we wish to reset the heat map canvas, we simply click the Reset View button at the bottom right of the interface to return to our overview state. To clear the heat map canvas and allow for new group inputs, we click the Clear Data button. SpectraMosaic, when used in clinical research settings, can contribute in the assessment of individual variability, variability across time and space, and to understanding the complexity in the data beyond inference on statistical mean values. This constitutes a novel approach to investigating MRS data.